how to see the power of recursive algorithm. Here we use one example. Yeah. So this example, many of you, I think most of you, saw before. Tower of Hanoi problem, the puzzle problem. Yeah. So this time we will use recursion to solve this problem. All right. First, look at the rules. There are 3 rules we need to follow to solve this puzzle problem. The first rule, only one disk can be moved at one time. Okay? Yeah. So we count the number of steps, number of moves. Yeah. The first move, second move, every time you can only move one disk from one peg to another peg. Yeah. Rule number 2, a disk cannot be placed on top of a smaller disk. Yeah. For each peg, when you have a stack of disks, you should always place smaller disks on top of larger disks. Okay? Yeah. In that order. Okay? In that order. Yeah. Follow that order requirement. Rule number 3, all disks must be stored on the peg except while being moved. Yeah. This third rule, that means you cannot, when you move, you just play your disk on the table. Yeah. That's not allowed. Okay? So you have a lot of space you use on the table, so you put there temporarily. Yeah. Then it's too easy, right? Yeah. So the third rule does not allow you to do, other things or, on other places. So you always, at the end of your move, you always need to place a disk on one of the 3 pegs, and also following all the other rules. Yeah. All right. Under these 3 rules, we need to solve the problem. So in this diagram, you see we have 3 disks. So the problem, this puzzle problem, it's a 3-disk problem. Yeah. But our goal, we need to solve n-disk problem. Okay? Yeah. 3-disk problem, relatively easy. Yeah. So we need to solve the n-disk problem. Okay? Yeah. Any positive integer n, 10 disks or 100 disks even, you need to give a solution. Yeah. So that's not easy, right? Yeah. All right. Yeah. So usually, when kids, play this puzzle problem, solve this puzzle problem, usually 3 disks. Yeah. Okay. Yeah. A little challenging, but it's doable, right? Yeah. All right. But you can think about if the number of disks grows, 4 disks, 5 disks, then it could be very hard, right? Yeah. All right. So now, let's do analysis. Yeah. How to solve this puzzle problem. All right. Yeah. So here, we use our typical problem-solving thinking here. Yeah. So when we solve a problem relatively hard, so here we consider n-disk problem. It's pretty hard, right? Yeah. So what is our commonly used strategy in this situation? The problem, very hard. When we start, what should we do? Yeah. Our strategy, work on simplest cases, right? Yeah. Yeah. So when we start, let's work on the simplest cases. Yeah. Here, the number of disks, is that the data size? Yeah. The data size is n. Okay. Yeah. So we treat the number of disks. That n is our data size. When the data size is large, then the problem is very hard. Now we reduce the data size to the very small number, then it becomes very easy to solve. So when we start, let's work on n equals 1 or 2. These two cases. That's trivial, right? Yeah. One disk. Yeah. So you just move it, one move. You place it on the destination peg, then you're done, right? Yeah. So here, let's treat this peg number 3 as the destination peg. Okay? Peg number 3, that's the destination peg. Okay? Yeah. The middle one, that's the temporary peg. Yeah, because we need to use it to temporarily place some of the disks. Yeah, to give us more room to manipulate the disks. Yeah, yeah. But at the end, we should move all these 3 disks on the destination peg, following the required order. Yeah. All right. Yeah. So 1 trivial, 2 even 2 also trivial, right? Yeah. Yeah. Hey, can you tell me how many moves you need for a 2-disk problem? 3. Good. Yeah. Yeah. It's very easy to see it. 3 moves. Yeah. All right. Yeah. So now, yeah, the first 2 simplest cases, so easy. So now we need to consider size 3 problem. Then it's not trivial, right? Yeah. At least we need to do a lot of work. Size 3. Yeah. But let's recall our introduction to recursive algorithm, our Monday's class. Yeah. Our Monday's class, when we use the recursive thinking, yeah, when we work on the problem of current size, here the current size is, size 3 is the current size, right? Yeah. When we work on the problem of the current size, we can assume the subproblems of smaller sizes have been solved, right? Size 2 problem have been solved. Size 1, size 2 problem have been solved, yeah? So that's our recursive thinking. Yeah. That means when you solve the problem of size 3, you can use the solution of the problem of size 2. Yeah? So this is the, essence of the recursive thinking. Yeah. Because in this way, you do not start from scratch. Yeah. Your starting point is the solution of size 2. That's your starting point, right? Yeah? So you only need to do the, get the last disk, that part done. Yeah? Yeah. Because you already have the size 2 solution. You can build your size 3 solution on top of the size 2 solution. So you need to do some extra work. That part, if you can fix it, then you solve the whole problem. So that's our recursive thinking. Yeah. All right. Now, based on that, that understanding, so let's consider size 3 problem, n equals 3. Yeah. All right. So this time, we need to work on it, right? Yeah. So, because in our mind, solving a problem relatively hard, we only do the work in our mind. It's very hard to keep track of the data, right? Yeah, too messy. We get lost. Yeah. So due to that reason, we want to do experiment on paper. Okay. Yeah. So on a board. Yeah. Yeah. So here, diagram. We need to use diagram to show step by step moves. What is the first move? What is the second move? And so on. Okay? Yeah? Yeah. All right. 0, that's our, starting point. Yeah. First move, the smallest disk, we move from the first peg to the third peg. Yeah. One move. Yeah. Very easy. Yeah. Second move, the middle disk, we place it on the middle peg. Yeah. Okay. First two steps, pretty straightforward. Yeah. Yeah. All right. Then the third one, because we cannot move the largest disk, right? Because not allowed to place it on the second peg or third peg. Both violation. You cannot place larger disk on top of a smaller one, right? Our rule number 2 does not allow it. Yeah. So the third move, you can only move one of the two disks, right? Yeah. All right. Yeah. So our third move, we move the smallest disk back to on top of the second smallest disk. Yeah. That's allowed. Okay. All right. Yeah. So after this move, we need to think about it before we do the next move. We need to think about it a little bit. Yeah. The state, the current state. Yeah, let's look at the current state. What do we get at this point? The current state. Okay. We move top two disks from one peg to another peg, right? From one peg to another peg, but only top two disks. Yeah. Excluding the bottom disk. What's that? Yeah. Yeah. So at this point, we did something, but what did we do? Yeah. We need to describe it. Solution. Is that size 2 solution? Yeah. We apply size 2 solution, right? Yeah. Yeah. Because if you ignore the bottom disk, we just solved the size 2 solution, right? Yeah. If you see this point. Yeah. All right. Yeah. So that's the starting point of our new size 3 solution. Because size 2 solution, that's the old solution, right? You can treat it as we just apply size 2 solution. Now we need to do the extra part for size 3 solution, right? Yeah. So if you have this understanding, because you try to fit into the recursive thinking framework. Recursive thinking framework. Yeah. We try to, fit into it. Yeah. Recursive thinking. Yeah. Now, the extra part, on top of size 2 solution. Yeah. You move the bottom disk to the destination peg. Yeah. Okay. Yeah. So you have to do it. Yeah. Yeah. All right. Yeah. So we use P of 2 represent size 2 solution. P of n, that is our n disk solution. P of n. Yeah. That's our ultimate goal, right? Our ultimate goal is to find that P of n solution. All right. Step 4. Yeah. So then you place the largest disk on the destination peg. Okay? Yeah. After that, To complete the whole solution, basically you just need to move the top 2 disks back to the destination pad, right? Yeah. So that whole package, okay, moving top 2 disks from the middle peg to the destination peg, that whole thing putting together, is that a solution of P of 2? Size 2 solution, right? So here you can see the remaining work, you only need to apply the size 2 solution another time. Okay? Yeah. Although the starting peg and the ending peg could be different, yeah. But the pattern of moves should be the same, right? Yeah. All right. Yeah. So after that, you can see you need to apply size 2 solution the second time. Okay? Second time. Yeah. The first time and the second time. Okay? In the middle, you move the largest disk from the starting peg to the destination peg. Okay? So that's your understanding of the whole problem. Yeah. All right. Then, so number 5, yeah, the smallest disk from middle peg to the first peg, yeah, yeah. So that's another size 2 solution, but you use different starting peg and a different destination peg for size 2 solution. Yeah. Then, yeah, step number 6, move the middle disk to the destination peg. Then the last step, yeah, the smallest peg to the destination peg. So you solve size 3 puzzle problem. Okay? That's our experiment. So we can visually see the work, the details of the work. We can see it visually. Okay? And we can understand the whole process better, right, in this way. Yeah. Yeah. All right. Yeah. But after we solve the size 3 problem, now we need to go to the size n problem. Yeah. Yeah. Here we need to use abstraction. Yeah. So in problem solving, another important skill you need to develop, abstract thinking, is very important. Abstract thinking. Yeah. So that's a important capability you need in problem solving. So what kind of abstract thinking? Because you need to do the similar work, you need to generalize the process we just completed for size 3 problem to size n problem. That generalization, you need some abstract thinking to make it. Yeah. Yeah. The reason is because nobody can really work on size n problem, right? Yeah. Too complicated. Size n problem, too complicated. Yeah. So in your thinking, you need to use abstraction to handle that, fuzzy part. Yeah. So there is, fuzzy part. Yeah. Not very concrete. Yeah. Yeah. Because nobody can work on size n problem directly. Yeah. So you need to use some logical understanding to make that part. Okay? Make that, fuzzy part. All right. So let's move to the size n solution. Our final goal, we need to solve the problem for the n disk case. All right. Solve the general case. This time, we need to really apply the recursion explicitly. Yeah, explicitly. All right. Recursion. Yeah. So here you can see, after we have the background of recursion, from our introduction to recursive algorithm, we have that background. Now we need to use our background here. All right. Yeah. Later you will see, yeah, solving this relatively hard puzzle problem. So we really need to apply the recursive thinking. Yeah. Yeah. Otherwise, too hard. Yeah. All right. And yeah. Here, yeah, another thing in our understanding, we can say, why in this situation the recursive method helps a lot. Yeah. Because recursive method, inside the recursive algorithm, there is an important work we do, that is the problem size reduction. A current problem, the size is relatively large, but we can use the solution of some previous sizes. Yeah. So that will be easier, you know. So size reduction approach. Size reduction approach. Yeah. So that understanding, yeah, very useful in this situation. All right. So now, yeah, specifically, so what kind of size reduction, right? Specifically, yeah, because we have many different ways to do size reduction. Yeah. Divide and conquer, right? Divide and conquer. When we divide the problem, we have many different ways to divide the problem, right? Yeah. So here we use one special way to divide the problem. Size 1 reduction. Every time we just reduce the problem size by 1. Okay? Yeah. Similar to our factorial problem, right? So, yeah. When we use the recursion to solve the factorial, we reduce the problem size by 1. Every time, size 1 reduction. Yeah. Here you can see we do the size 1 reduction. All right. Yeah. If the current problem size is n, we assume the problem of the previous size, n minus 1, has been solved. Yeah. We assume that. Yeah. Okay? We assume that. Yeah. All right. That, because when you do that assumption, so it's a reasonable assumption, right? When you do that assumption, you can greatly reduce the difficulty of the problem. So the problem won't be that hard because you only need to address the difference between two problem sizes, right? Yeah. Yeah. Because when you make this assumption, the amount of work you are going to do won't be that scary. Too much work. Yeah. So make it very scary. So the amount of work you need to do is, yeah. So currently, this is our goal, P of n. But you assume P of n minus 1 has been solved, right? Yeah. So what you need to do, just fix that gap part. There is a gap between these two adjacent problems, right? Yeah, two adjacent problems. There is a small gap. So you only need to put your effort on the gap of two adjacent problems. So that's our understanding of recursion. Okay? If you can make it, yeah, fixing the gap part, then you solve the whole problem. Yeah. Yeah. So that's very nice. Yeah. Yeah. So this kind of logic, very powerful, right? Yeah, very powerful. Yeah. All right? Yeah. Try to get used to the thinking like this. Yeah. The thinking like this. Very powerful. Yeah. All right. Now we follow this plan. This is our plan. So we want to complete the generalization step. Yeah. So here, yeah. Try to really feel about the problem solving. Okay? Yeah, the process, the details. Yeah, let's do the work. Yeah, but we need to you know, on paper, so because that's still pretty complicated. So we need to do the work on paper, All right, this time we still use the, part of the diagrams we used before. Here, although you see 3 disks, but we just imagine we have n disks on the starting peg. We treat it. So this whole stack contains n disks. By our imagination. Okay? Then, next step. Because we assume P of n minus 1 is available. The solution of P of n minus 1 available. We can apply it, right? When we apply it, we move the top n minus 1 disks from the first peg to one of the 2 other pegs, right? That's the P of n minus 1 solution. Okay, all right? So now, when we do the work for P of n minus 1, we need to solve P of n minus 1 first. We need to apply the solution of P of n minus 1. And we assume we have it, right? Based on the recursive thinking, we assume we have it. No problem. After you understand how recursion works inside computer high-level language, so you have the confidence for this step, right? Otherwise, people may ask, why you can't assume this, right? You assume too much. Some people may argue, so in this step, you assume too much. We know our assumption is reasonable here. Why? Because last time I explained how the recursion works inside main memory, right? I explained that. So after you have the background of that, you should have the confidence. So this step, we do not have any problem. We just do it. All right? So then, all right. Next step, so here, so I need to draw. I need to draw something here. The remaining part of the work, pretty straightforward. Because the next step, next move, you move the bottom disk to the destination peg. Okay? All right. After that, after that, you just apply P of n minus 1 another time, right? Then you get it solved. You get it solved. So, to complete description of P of n solution here, so you need to use a little bit abstract thinking, a little bit. Okay? Abstract thinking, not too much. Just imagine, right? This n disk, you have no problem. You treat this 3 disk stack as an n disk stack. Okay? So when you move, top n minus 1, you have no problem to make that move, right? So that kind of abstract thinking. Okay? You need that. Okay? You need that. If you feel very comfortable in that abstract thinking, then you have no problem to complete the whole solution. Although it's pretty complicated. But after you address several critical steps, then you have the understanding of the whole solution. How about this process? That's the whole solution. Okay, all right. So after we have the visual understanding on paper. Now let's move to the pseudocode. Yeah, we need to write the code, right? Yeah. So we need to write an implementation code. Yeah. Here I use the pseudocode way. Yeah. You can see the implementation is pretty straightforward. Okay? And pretty short. Yeah. Here we solve an n disk problem. Yeah. Yeah. I here use the C++ style. Move disks. Yeah. This function does not return any output, so it's a void function. Okay? So we only do data processing. Yeah. It does not return any output. Yeah. The input, 4 parameters. The first one, number of disks. Second, integer number as the number for the from peg. Yeah, from the variable parameter name. So from peg. Okay. Then the destination, the third parameter integer to peg. That's the destination peg. Yeah. Then we need a temporary peg. Yeah. So in this order. So we manage the data in this order using these 4 integers. That's good enough. Okay? Yeah. To describe this problem, we get sufficient information to complete the whole solution. Yeah. All right. So when we do the work, if the number of disks, that number is greater than 0. Yeah. If it's 0, nothing, right? Yeah. So we can terminate the program immediately if number of disks number is 0. Yeah. But if it's non-zero, now we can apply the recursive implementation. The first step, we call this function recursively, move disks for n-1. Okay? The previous solution, n-1. But we need to carefully set the numbers for the 3 pegs. Okay? Yeah. From peg, the destination is the temporary one. Okay? Yeah? So the destination is the temporary one. Then we use the 2 peg as the current temporary peg. Yeah? Yeah, so, yeah, based on your visual understanding, you can fix this problem, this step. Okay? Yeah. After that, you need to move the bottom disk. How do you simulate this place? You need to simulate the move, bottom disk move step. Simulation. Yeah. So your simulation is you just print out a message. Okay? Move a disk from peg, yeah, from peg number to peg number, yeah, then, data. That's your move. Okay? Yeah. All right. Yeah. Move. Yeah. After that, then you need another recursive function called move disks. Still, the n-1 disk problem, the solution, but you need to carefully set the 3 parameters for the 3 pegs. Okay? Yeah. So the the starting peg for the n-1 disks. Yeah. So the temporary, temp peg, that number, you use it as the starting peg. Okay? The 2 peg, so your destination peg is the same. Yeah. Then the from peg, you use it as the temporary peg. Right? Yeah. So here you can see, the main steps, not that hard. Yeah. The structure, pretty clear, but when you write the code, you need to be very careful to set the 3 numbers for the 3 pegs correctly. Yeah. If you can fix that kind of details, then you complete the solution correctly. Yeah. So that's the whole solution. Okay? Yeah. All right. Here, after the discussion for this puzzle problem, Now we need to do some summary. Yeah. Yeah. From this example, can you see how powerful the recursion is? Yeah. Think about, without recursion, can you solve this problem? Yeah. Without recursion, if I ask you to use for loop, yeah, because we use iteration, right? Without using recursion, we can use iteration. Then how hard it is. Yeah. You can only use for loop, okay? Extremely hard. Yeah. Okay? Yeah. Extremely hard. So we cannot imagine that. Yeah. So here you can see recursion provides us a powerful tool in problem solving for computing problems. Okay? Yeah. So that's the reason. Although we need to use a lot of memory resource in order to apply recursion, but we're willing to pay that much cost, right? Yeah, we're willing to pay that much cost, right? Because the gain is huge, right? The gain, so we can solve pretty hard problem with such a very short code, right? Yeah. Just a few lines. You can solve such a hard problem. Yeah, so that's the power. Yeah. Yeah. Here's just one example. Yeah. There are many other examples we need to use recursion to solve. Yeah. Right? Yeah. So, yeah. So that's one in our summary. Yeah. Okay. Another point. Yeah. So because at the end we also want to know the number of moves solving this puzzle problem of size n. How many moves do you need to make? Yeah, yeah, yeah. So that question, yeah, yeah. It is a question here. Yeah, we need to do some work to get the answer, but that question, so we'll delay to later sometime. Yeah. Later, when we need to solve recurrence equations at that point, yeah, our part D, we will, look at the problem, how to solve recurrence equations. At that time, we will solve this problem. The number of disk moves, yeah, so this one first. So then we will solve another harder one. Yeah. All right. Yeah. Yeah. So we finish part A. Yeah. Next, let me move to part B. Yeah. First, let's look at the problem. Problem number 8. Count binary digits. Number of bits, binary digits. Yeah, we call it bits. Okay. All right. So the problem is pretty simple. Yeah. Given a positive decimal integer n, yeah, and find the number of binary digits in its binary representation. So we can write it using a binary system, binary representation. Then the number of bits. How many bits do you have, right? Yeah. Yeah. So it's a pretty simple problem, yeah, but we need to do a special type of recursion in this case. Yeah. All right. So let's look at try to understand this problem. Yeah. The structure we need to understand. Yeah. The structure of the data first. Yeah. The data, yeah, integer and one number, and we know the data size is the magnitude of this number. All right. First, let's review the binary representation. Yeah. Here, yeah. So this part, we need to use our background in discrete math. Binary representation, yeah, in discrete math. There is a standard way to represent given integer m in the binary structure. Yeah. The structure is like this. This is the standard structure. For the numeral system, okay, here we use the binary system as the current numeral system. Yeah. All right. N equals, so the coefficients part, B0, 1, 2, 3, yeah, these little b coefficients, that's the values for the bits in different positions. Yeah. Different positions, okay? All right. Yeah. So then, the base part, yeah, power of 2, that's the base part. Okay? Yeah. Yeah. So B0 corresponds to 2 to the 0 position. B1 corresponds to the 2 to the first position, and so on. Okay? Yeah. So that's the standard structure of the binary representation. Yeah. Yeah. All right. And we need to assume the most significant bit, B sub s, not equal to 0. Yeah. Otherwise, we can remove this term, right? If B sub s equals 0, we can remove this term to simplify it. Yeah. So we can assume that. Yeah. All right. So based on this structure, now we need to do the data manipulation. Yeah. So do the transformation. Yeah. We do transformation on this formula. So this is our current main formula we need to work on. Yeah. Here you can see in problem solving there is one important step. The first step, representation step. So we need to find appropriate representation, this step. Otherwise, how do you work on your data, right? So if you cannot represent your data correctly, you don't know how to work on it. Yeah. All right. Now let's do the transformation on this formula. Yeah. All right. Here, the goal, we want to count the number of bits in this binary representation. Yeah, because we assume the most significant bit is non-zero, then we can count the number of bits easily. That's s plus 1, right? Yeah. There are s plus 1 positions. S plus 1 different positions. Yeah. So then the counting number is s plus 1. Yeah. So we know, based on the fact, this is the answer, s plus 1, but we cannot use s plus 1 as our final answer directly, right? Yeah, yeah. Because our given data is n. This s in the formula here, it is the temporary variable, right? Yeah, that little s is a temporary variable. Yeah, you know. So when you provide your final answer, you should use the given data, input given data, n. So you should write your answer in terms of n, not in terms of s. Yeah. Yeah. So that's the reason. So we haven't complete our solution. Yeah. 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 So we get part of the solution, s plus 1. That's the partial solution, but not final solution. Okay? So we need to represent little s in terms of n. Then we are done. Yeah. Then we are done. If we can write little s in terms of n, that's our final answer. Okay? Yeah. Yeah. The question, how to write little s in terms of n. Yeah. So we need to do some work on this main formula here. All right? Yeah. In order to find S, we need to, change the form of the original formula. Yeah. Yeah. Change the form of it. Yeah. And see what can we get. Yeah. All right. Yeah. So the next step is critical. Yeah. Yeah. How do you change the form? Yeah. Critical. Yeah. All right. So here, when you change the form, you need to take advantage of the structure of your data representation. You need to use the properties of the structure. Okay? Yeah. Yeah. All right. So here, the property of the structure, one important property here, you use power of 2 to represent your terms. Power of 2. Now, each term, you write it as a power of 2 times some coefficient. Yeah. Yeah. So that's the property. Okay, all right. Yeah. Then, this step is critical. Yeah, so we call it inside, critical step. Yeah. All right. So, to do that, you need really some problem-solving imagination. Yeah. All right. Yeah. Here we need to apply division operation to do the transformation. Division by 2 operation. Yeah. The base number is 2. So when we do division by 2, basically we maintain the same structure, right? Yeah. Yeah, because when you do division by 2, the right-hand side still sum of terms of power of 2, right? Yeah. You do not change that structure. Okay? Yeah. So that's why we do division by 2. Yeah. Division by 2, when we do it, yeah, we want to only we keep the integer part. Yeah. We do not keep the fractional part, integer part. So the left-hand side, we need to take floor function. Yeah, because there is a possible 1/2 left. So we don't want to keep that. Yeah. So when we do division by 2, we take the floor function both sides, but when you look at division by 2, other than the first term, B0, all the other terms, they are multiples of 2, right? Yeah. So for all the terms except the first one, you don't have the fractional part. Yeah. You only have the integer part. But the first term, you may have the fractional part, right? When B0 is 1, you have the fractional part. But you just drop it. Yeah. Throw away. Yeah. Yeah. No matter B0 is 0 or 1, it's gone, right? Yeah. After you take the floor function, it's gone. Yeah. So that is for after this transformation, you get a new binary representation, but this time you get a binary representation for n/2 floor function. n/2 floor function, the current binary representation. Okay? All right. After that, then you compare the difference between, this time you have 2 binary representations, right? Yeah. The first one, second one here. So you have 2 different binary representations. Now you want to study these 2 representations and look at the difference, compare the difference. Okay? All right. The first binary representation corresponds to the data size n. N is the data size. Yeah. The magnitude of the given number data size. Yeah. For the second representation, n over 2 flow function, that is the data size. Okay? Yeah. So here you can see the data size of the second formula is approximately 1/2 of size of the first data size. So that relationship. All right. Then you can count the number of bits for the second formula easily, right? Yeah. Yeah. How many bits do we need to represent n over 2 flow function? S, right? Yeah. If you use S, yeah. Here we are allowed to use S because in the intermediate steps we can use temporary variables, right? Yeah. In our final step we cannot use temporary variable, but in our intermediate steps, yeah, we can use temporary variables. Yeah. So the number of bits for n over 2 flow function, that's S. But the number of bits for n representation, binary representation, it's S plus 1. The difference is 1, right? Yeah. Difference is 1. Yeah. So this relationship, yeah. So we want to use this relationship to help us find our final solution. Yeah. All right. Yeah. So let's write this equation. Yeah. All right. Yeah. Based on this observation, yeah. All right. Yeah. You know, the least significant, that's B0. It's removed. Okay. Yeah. Yeah. It's gone. Right. Number of bits reduced by 1 from S plus 1 to S. So the value difference is 1. Yeah. All right. The problem size reduced by half, yeah. Approximately half. Yeah. So we can call half, okay? Yeah. Because in our computer science, approximation is very common. Yeah. So, yeah. Not like math. In math, people like to use the accurate representation. Yeah. But in our computer science, especially when we deal with large data, so we like to use approximations. Yeah. So here, approximately the data size by 1/2. Yeah. Size reduction, 1/2. It's a good approximation, right? The difference is possible 1/2. Yeah. Difference. Half integer. Yeah. Yeah. That difference is so small. Yeah? So we will be very happy. That small difference. Yeah. All right. Yeah. Then our recursive formula. Recursive formula. Yeah. So we need a function. Okay. Yeah. Yeah. Binary recursion, right? Yeah. Of n. So this function, its value of n, the number of bits, binary bits, number of bits used to represent n equals the number of bits used to represent flow function of n over 2, then plus 1. Yeah. So you do a recursive function call to get some value, then you add 1, then you get the value for the solution of the current problem size, n. Yeah. So this recursive formula tells us that meaning. Okay? Yeah. So next, yeah, we need to have a base case, right? Yeah. So when n equals 1, so you count the number of bits, also 1. Yeah. That's the base case. Yeah. So then you can find a solution. Yeah. Here, you can find a solution. All right. The next step, we need to solve recurrence relation. Now, we need to find a solution. Okay, all right, yeah. So because for the problem solving, we need to complete the whole solution. Okay, all right. So next, yeah. So here, here I just first we look at the division by 2. Yeah. So here, yeah, in our implementation, you can see we need to do division by 2 operation, right? Yeah. So division by 2 operation inside the computer, it uses the left shift operation. Left shift, right shift. Yeah. In C++. So you can have that, the arrow, right? So, from left shift, right shift. Double arrow, shift to the left, shift to the right. Because when you do this operation, although it's a division, you do this operation extremely fast. Yeah. So why? For some of the students, so they may not understand why people need to use left shift or right shift operation. The reason is really fast. Yeah. So here, it's faster than an addition operation. We know addition operation already pretty fast, right? But you need to do a lot of work, right? When you do addition, bits by bits, you need to do a lot of operation. But shift, you just move the, binary point, right? You move the point extremely faster when you do addition, right? Yeah, think about that. Yeah, so much faster. Yeah. And here also another background information I'd like you to know. Yeah, because in our mind, we know response time, reduce the response time, very important, right? Yeah. So when we do our implementation, yeah, so we try our best to reduce the response time. Yeah. So this is one place we can do to reduce the response time. Yeah. Let me record, give you some idea about the operation. Yeah. Yeah. Addition first. Yeah, addition. Yeah, so here I use addition, okay? Compare with multiplication. Yeah. Then compare with division, okay? Yeah. For integer data here. Give you some idea. The response time difference. Yeah. That's the ratio of 1 to 10 to 40. The typical scale in that much difference. That means if the addition operation uses 1 unit of time, integer addition, when you do integer multiplication, you need 10 units of time inside CPU. Okay? Then when you do division, regular division, you need 40 units of time. That's huge. 40 to 1 ratio, right? Division, compare division and addition. 40 to 1. Okay? Huge difference. Yeah. But that's the regular division. Okay? So if you do division by 2 using the regular division, you need to use 40 units of time. That's too much. But if you do the left shift, that division by, it's faster. It's less than 1 unit of time. Faster than addition. Right? Yeah. For that reason. So when you do division by power of 2, you just move the, binary point. Moving points so fast. Okay? Yeah. Yeah. All right. Yeah. Then, now, we try to solve the problem. Yeah. So here we try to simplify this function slightly. So we define a function, a of n, as the number of additions. Because when we do +1, you know, we do some addition operation, right? Yeah. All right. So here we can use that number of addition, that operation. Yeah. So here, yeah, in this way. Yeah. 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 Equivalent. Yeah. So another recurrence relation, but you know, equivalent to the original one. Yeah, but here, you know, our notation just slightly simpler. A of n equals A of floor function of n over 2 plus 1. Yeah, because after you get the number of additions for the size n over 2 floor function, then you do one more addition, you just get the number of additions for A of n. Okay, then the initial condition you still use 1. Okay, all right. Yeah. All right. Yeah. So next, let's solve the simplified version. Okay. Yeah. So, all right. Now let's do analysis. How to handle the floor function? Yeah. So when you solve this recurrence relation mathematically, so here I'm talking about we want to find a solution mathematically. Yeah. Because at this point, we can already write a code to calculate the value of A of n by a program, right? Yeah, so easy. Recursion. Yeah. Yeah. All right. Yeah. But because this recurrence relation relatively simple, we want to solve it mathematically. Okay? If we can solve it mathematically, we have a formula for the final result. When we apply the math formula, it's even faster than the recursion, right? Yeah. Yeah. When we apply math formula, that's the fastest possible way to get a final answer. Because when you apply recursion, you still need a stack, right? Internal structure, you need to have a stack. You need to still do a lot of calculations. But math formula, we plug in, it's done. We just calculate the math function directly, without recursion, right? Yeah, no recursion. No stack, okay? Much faster, yeah. So that's why, if it is possible, we want to find math formula, all right? Yeah, yeah, yeah. We run out of time, yeah. But we are at a point, we need to find the math formula as the answer, right? Yeah, so that part, I leave it next time. So next time we finish this problem, then we have another problem, okay, for part B. Yeah. All right. So after that, we may have some time. We can do part C. Okay? Yeah, part C. Yeah. Yeah. All right. Yeah. So that's it. Yeah. So this week, when you have time, try to work on the homework assignment as early as possible. Okay? Yeah. But at the same time, I will post the solutions to 2 sets of exercise. Yeah, so I post some of the questions are similar to our homework questions. So you can use to give you some, hints for the homework questions. All right, yeah, that's it.